Recorded is rolling. It is Tuesday, September 10th. I have a projectile lab lined up for you guys today. You guys got to use these launchers. I think I showed you guys these a little bit yesterday, but we're going to review how to use this first. It's got some technical details. Guys, got a ramrod, got a launcher. I do have a little squishy bouncy ball, but hang tight on that. Okay? Oh, guys, listen real close. You hear some clicks. You guys hear it click? Right? Oh, but look at this short, medium, long range. Click. Oh, medium. Third click. It's gonna go a long way. So I really just spring loaded this thing. I really set the spring. Now if I release if I pull this, it'll release it. There it goes. Okay. Get the set again. Guys, what do I want to do first? Do I want to put the squishy ball in first and then ramrod it and the ball gets stuck? Do I want to do that? No. Do I want to ramrod it first to get it set and then take the ramrod out and then put the squishy ball in? Yes. Yeah, that's exactly it. There it goes. Oh yeah, just like that. So you guys see how to operate the launcher? That's pretty much it. And your guys' goal today is to figure out how fast is that firing? How fast? Thank you. What's the launch speed? Okay. So there's different setups that you can do. I'm kind of directing everybody towards this one particular method. So we're all on the same page. We're all following the same equations by the end of class. Right? But hey, maybe that's a good question, actually, is to think, well, how could you do this lab in principle? Like, can you guys think of maybe a setup that I did not draw here? How could you fire this launcher some way to ultimately be able to determine the launch speed? Well, this. Last couple of classes, students have been saying, hey, what if you aim it straight upwards and fire it straight upwards? How? It goes to some maximum height. You guys think from that maximum height, you can determine how fast it was being blasted out here, V? Right? Yeah, you could do that. Right? You have to know Earth's gravity field. You're allowed to know that today too. Right? What about this? What if you aim it off on some angle and you measure, so call this V blast right here, right? And you measure this angle theta, and it lands some distance like way out here. Maybe I'll call it X, some distance X. Okay? Guys, if you know where it lands, you know the angle you launched it at, do you think there's enough information there that you could also determine the blast speed? Okay, you could do that too. Now that one's probably one of the trickiest ways to do it. So I'm not gonna have you guys do it either of these ways quite today. Okay? Oh, somebody said this too. I wasn't thinking about this earlier until somebody said it. Right? Is what if you just launch it and just put a speed gate like right in front of it, and the ball just goes immediately through a speed gate? Right? Yeah, that'd be a way to do it too. All right, but I'm directing everybody towards this method where you put the launcher right on top of a balcony. We're gonna head out to a balcony here in a few minutes, and you just aim it straight horizontal, okay? and then just launch it there, and just see where's the ball land? Spot where the ball lands. Ooh, guys, look at this dashed line path right here that the ball's gonna follow. Guys, what shape path is that? It is a parabola. Aha, it's a parabola. Right? Lots of parabolas in this class. Probably makes sense how it would show up again. All right, so determine the blast speed of the launcher. Your only measuring tool is a meter stick. Or actually, some of you guys have some trundle wheels. Do you guys know how to use the trundle wheel? Here, I'm gonna borrow one of these trundle wheels just so I can demo this in front of the camera here. Okay. And so you got this wheel on a stick. You guys can roll this across the ground. And, ooh, guys, take a guess. What do you think the circumference of one of these wheels is? 1 meter, exactly. So every time it makes a revolution, that's another meter. And on the other side here, hey, look, it's an odometer. It'll add up. So right now this says, think through this is 1.2 meters. I think you guys can figure that out. Right, the odometer. It's back to you guys. Don't have to use that. You can. That could be helpful. I don't want anybody using a stopwatch to measure time, although you're going to have to determine the fall time. That is part of this, but don't use a stopwatch because this is not a very accurate method. Trying to figure out when to start, stop. Okay. Instead, if you calculate the amount of time based on this drop height, it'll be a lot more accurate. You think about that, but I'll do a little bit of that later. Right, so your only measuring tools really are for distance, meter stick, trundle wheel. Okay. I'll go ahead and give you guys the mass of a ball. I measured a bunch of balls last night. They were all 7 grams. So let's just call it 7 grams because I mean, that probably would make a difference, right? There's different mass balls, but we're just going to keep that as a control, put that to the side. You're also allowed to know Earth gravity. So pick your favorite number. You can use either one of these for Earth gravity. They'll give you about the same answers at the end. Okay. All right, so there you go. There's the setup. Right before I hit record, a bunch of guys were already copying down this table, which is good. All right, so we've got different trials going on. Measure what is this drop height in meters, which is probably just the same number all the way down. So once you measure it once, it's just me, same drop height. This horizontal displacement. Spot where the ball lands. How far has it moved horizontally while it was being in a projectile? So guys, here's a issue that's come up a few times today. Do you want to spot exactly where the ball lands and then measure to that point? Or do you want to let the ball roll, and just measure how far it rolls? What makes more sense? Yeah, where it first landed, definitely, right? Because that's the only part that was a projectile, and all these projectile equations are going to actually matter, right? Yeah, so just spot where it lands, right? Notice above the columns, I said whether you're measuring or calculating something. Those are your only measurements, really, is how far did the ball drop and how far did it land? Right? If you also know the gravity field, there's enough information there. You can figure out how fast it was blasted. Right? There's definitely determinable some blast speed. Right? Now, one of your calculations is going to have to be, well, how much time was it falling for? Here's why you want the time. Because if you know how far across it went, its horizontal displacement, which I'm calling d, and you divide by that time, doesn't that tell you its horizontal speed? Which, if you aim the launcher horizontally, is also the answer to the lab. That's also the blast speed. You guys see the blast speed and the horizontal speed are going to be the same thing. You guys see that? Right? Okay. So, okay, so you got to figure out the fall time, but how are you going to figure out the fall time? Well, how about this? As long as the launcher is aimed horizontally, then guys, what is the initial vertical velocity of the ball? Zero, right? When the ball's leaving the cannon barrel, it's not moving up or down, not during the first like nanosecond. So yeah, so initial vertical velocity is zero. Hey, how about this? What if you launch a ball to the side and you drop a ball at the same time? Which one's gonna hit the ground first? Same time, they tie. And what if you blast one kind of slow and you blast one kind of fast and you drop the ball? Which one hits the ground? They all tie, don't they? They all tie, right? Which means they all have the same vertical motion, which means that you can determine the fall time knowing only the drop height and the gravity field. That's all you need, right? You guys think you can figure that out? Right? Actually, I think you guys did that about a week ago. You guys remember pairing up, one of you dropped a roller, the other caught the roller, said, oh, it fell like so many centimeters, I can calculate my reaction time. I think that's going to be embedded in this lab. Right? Let me go ahead and show you guys this. When you guys come back and you're making some calculations, figuring this out, I'll throw this up on the screen too. Right? But I found over the course of the day, it's worth seeing this twice. Right? Now so you can think about it, and then later on, you're like, oh, okay, it looks a little bit better. Right? So here I've got red ink, green ink, and then black ink. It's like step 1, step 2, step 3. It was really this whole calculation bit. Right? So see if I know the drop height, that's going to be equal to 1/2 GT squared. Hey, is that the college equation? Been falling for 5 seconds. How far did it fall? 125 meters. How'd you know that? College? Is that the college equation right there? Right. Now, if you know the drop height, because maybe you take a meter stick and it's 1 meter, 2 meter, 3, so many meters tall. Or maybe if they gave you a rope, you could lower the rope and then measure the rope. That'd be another way you could do it too, right? Then, hey, do you think you could calculate what the fall time would be? And you're allowed to know the gravity field, of course, right? So say algebra. Hey, isn't that right there the answer to your reaction time lab? The roller fell so far. I know Earth's gravity pull. I can calculate my reaction time. Only this time it'd be the fall time of the ball. You guys see that? Okay, so all the red ink is just vertical information. That's step 1. Right? Let's skip over to the green ink. This is the horizontal information, step 2. So how far did the ball move horizontally? Right? Well, wouldn't that just be its horizontal velocity times the time that's a projectile? Right? Distance equals speed times time. Right? Hey guys, is it moving across the field at constant speed? I think it is. Because does gravity pull horizontally? No, gravity only pulls vertically. Gravity only pulls down. And there might be a tiny bit of air drag, but we're going to call that negligible. So air drag, we're just ignoring anyway. Yeah, so the ball goes pretty well constant velocity across the field. Right? And if that's true, if you know how far it went and how much time that took, because it's the same time here to here, whether you think about it horizontally or vertically, right? All you have to do is divide those two, and that tells you how fast. And that's the answer. That's the entire thing. Right? Oh, now since the fall time is this whole fun fraction looking expression, you can put this all into one expression, one giant expression. It would look like this. Is if I have a fraction within a fraction, I have something divided by a fraction. Can I take the denominator fraction and flip and multiply it? That's where this comes from, this bit right here. That's why it looks like that, kind of upside down of that. You guys see it? Right. Right. So this black ink box, this is like the master answer to everybody's lab. Again, over the course of the day, I found out it's good to actually show you this ahead of time, and then you guys get to see this the second time later. Okay. Right. So that's a big picture force for the trees. How you guys are thinking about this? Of course, you guys can chunk this into smaller steps. You can solve for the fall time, and then do the calculations. Right. Okay. Speaking of fall time, which is of course one of your middle calculations, what makes more sense? Suppose I got 3 different teams that all disagree. One team says it takes about 10 seconds to fall off that balcony out there. Another team says no, it takes pretty close to 1 second. Another team says no, it takes about 0.1 seconds. Because what sounds most correct? 10 seconds, 1 second, or 0.1 seconds? Yeah, it's probably pretty close to a second. That might not be exactly the answer, but it's probably pretty close. Right? You guys think? All right, so just check your answers along the way. That's a good thing to do in physics. Make sure your answers seem reasonable. What you guys think? All right, so you guys ready to head outside? All right, let's head outside. We'll be back. Last about 10 minutes of class. All right, we're back recording. We last a couple minutes of class. You guys been doing your calculations, and I think you guys all got it. Guys, did you guys see the drop height was probably about 5 meters? Some of you guys got a little bit less. Some of you guys got a little bit more, depending on where exactly you launched it from, here, the top or the bottom of the gate. But you guys got about 5 meters. Guys, how much time does it take to fall 5 meters? 1 second. Right? So that was all this writing. You guys should have gotten a time pretty close to 1 second. Maybe got 0.95, maybe got 1.03. That was pretty close. Right? Now, however far it went. For looking at you guys' papers, you guys got about 6, 7, 8, 9 meters, somewhere in there. Suppose you got 8 meters. Guys, if it went 8 meters across in 1 second, how fast was it going across? 8 meters per second. Right? That should be pretty close to what you got in your lab. And you guys did pretty good, looks like.